Okay, so what we're going to talk about is we have a maximal interval of existence of a solution y of the ODE x prime equals f of x, the maximal interval of existence is the open interval alpha beta. When can alpha be greater than minus infinity? When can beta be less than infinity? And we talked about this at the end of class on Friday, and the idea was that if this happens, then either y of t goes unbounded as t goes, or as I should say, as t increases to beta, or t decreases to alpha, or y of t goes to the boundary of the open set, where the open set is the set where f is Lipschitz, is locally Lipschitz. So let me show you the theorem from the book, and then we'll talk about its proof. Okay, so here's the theorem from section 17.4. I think that's the right section. And it's the usual thing. We have f is C1 on the open set. This is the same thing as, this implies f is locally Lipschitz on the C1, although you're not responsible for knowing how to prove that. You need to know that. Don't worry about the proof. And we assume that the maximal interval alpha beta of the solution y has the right endpoint finite. And we'll assume that y of t, we'll assume that there's some compact set C contained in the open set O, so that the image of y is contained in the compact set, and then we're going to get to a contradiction. With alpha beta being maximal. And so that will then imply, that contradiction will imply that there is no compact set C, so that the image of the maximal interval is contained in C. And when I say no compact set C, obviously I mean there's no compact set C no compact set C in the set omega, in the set O. So the proof is going to go in a few steps. So first, we're going to extend the function y from alpha beta to the half open interval alpha beta. And notice that I'm referring to the function y. I'm not referring to any solution. And then second, we're going to show that at beta we have y of beta is equal to the integral from some point gamma to beta of f of y of s ds. And then 3, we're going to conclude that the left hand, the derivative from the left, exists at beta, and that y prime at beta equals f of y of beta. And then 4, we extend the solution from alpha beta to alpha beta plus epsilon by considering the initial value problem at t equals beta. And then it's step 4, which is the contradiction. Because that would mean alpha beta isn't maximal, is not the maximal interval. And just to be helpful, let me not refer to epsilon, but let me refer to A, because you're used to that in the local existence theorem. Okay, so that's the battle plan. So let's just go for it. Okay, so proof. Assume there exists a compact set C in the open set O, so that the image of the maximal interval of existence is contained in that compact set C. We know that F is continuous, and we know that C is compact. So that tells us that F is bounded on the compact set, so there exists some M which is finite, so that the magnitude of the vector x, the magnitude of f of x is less than or equal to m for all x in the compact set. Okay, so I claim that the function y is uniformly continuous on the maximal interval of existence. So y. Fix some point gamma in the maximal interval of existence. I'm going to center all of my, I'm going to write down functions relative to gamma. So y is a solution on alpha beta. Therefore, for all t in alpha beta, we have that y of t is equal to y of gamma plus the integral from gamma to t of f of y of s ds. Therefore, if I take 2 points, y of t minus y of t tilde, that's going to be the integral from t tilde to t of f of y of s ds less than or equal to min, max, it's the usual things, t tilde, t tilde of the magnitude of f of y of s ds, and this is less than or equal to m times the magnitude of t minus t tilde. Okay, so that does y is uniformly continuous. Okay, so because y is uniformly continuous on that interval, we know that the limit as t increases to beta, well, actually, of y of t exists. So you need to think about that. So why would the sequence y of tn be Cauchy if tn increases to b, beta? Alright, so the limit exists. Give it a name. Call it y of beta. So more specifically, what I'm saying is that we can extend the function y to the half open interval by y of t is equal to y of t if t is in alpha beta, and it's equal to the limit as t increases to beta of y of t if t equals beta. Alright, super. So now the question is, we have two options. So we have beta is finite, and before we had our function which was defined up to beta, and we then proved that we could fill in the dot, that there was a limit. But the question now is, could we have that y prime of t has its magnitude going to infinity as t increases to beta? So this right here is my attempt at y prime of t goes to infinity as t increases to beta, and here's my attempt at y prime of t is finite as t increases to beta. So just imagine that this is going to a vertical tangent. So pretend I can draw. Alright, so we have two claims. So I claim that y of beta is equal to y of gamma plus the integral from gamma to beta of f of y of s ds. And claim 2, I claim that y prime of beta exists from the left and equals f of y of beta. Okay, so let's work on the first claim. So we know that for each t in the open interval, that y of t is equal to y of gamma, that's the point that we pegged everything to, the integral from gamma to t of f of y of s ds. And so I take the limit as t increases to beta of both sides. The left-hand side goes to y of beta by definition of y of beta. And so we have y of beta is y of gamma plus the limit as t increases to beta of the integral from gamma to t f of y of s ds. So I claim that the limit as t increases to beta of the integral from gamma to t of f of y of s ds equals the integral from gamma to beta of f of y of s ds. So it suffices to show that the limit as t increases to beta of the integral from gamma to beta of f of y of s ds minus the integral from gamma to t of f of y of s ds equals 0. And so that's the limit as t increases to beta of the integral from t to beta of f of y of s ds. And I want to show that that equals 0. So I just do that by controlling the integral from t to beta, the magnitude of that. So that's less than or equal. I take the absolute values inside. I use the fact that f is bounded. And so now I have that the limit 0 is less than or equal to the limit as t increases to beta of the magnitude of the integral from t to beta of f of y of s ds is less than or equal to the limit as t increases to beta of m magnitude of beta minus t, and then I'm done by the squeeze theorem. Okay, so I have that y of beta actually equals y of gamma plus the integral from gamma to beta of f of y of s ds. Now, so I went from defining y of beta to showing that y of beta satisfies this equation. So now my question is it true that the left derivative exists at beta and equals f of y of beta? And so that means that I need to show that the limit is, how do I want to do that? Let's do it the other way. Okay, so I have two ways of writing this. One way to say the limit as h goes down to 0 of y of beta minus y of beta minus h over h, does that equal f of y of beta? The other way to do it would be the limit as t increases to beta of y of beta minus y of t over beta minus t. Does that equal f of y of beta? There's two different ways of writing the limit. The derivative from the left, you should make sure that you understand that they're the same. So the first one, you would want to show that the limit as h goes down to 0 of 1 over h y of beta minus y of beta minus h minus f of y of beta equals 0. And this will use the uniform continuity of y. And I use the Lipschitzness of f. On C when I did it. But you should actually do this as a homework problem, as a problem on your own. So work on your own on that. Okay, so now that we have that y prime of beta equals f of y of beta, we consider the initial value problem pegged at t equals beta. So let me draw a picture. We've gotten this far. So this is beta, and this is Rn. And now you're going to consider the initial value problem at this point. So you consider the initial value problem, x prime equals f of x at time beta is what looks kind of silly. X of beta is the red spot. So that is going to have a unique solution. So there exists A, and there exists a solution to the IVP on beta minus A, beta plus A. And let's call that solution y tilde. So we have y is a solution on alpha beta. Y tilde is a solution on beta minus A, beta plus A. They agree at t equals beta, so they agree on beta minus A to beta, and we've extended the solution. So that means we can extend the solution. And that's the contradiction, because the interval of existence was supposed to be maximal.